So here's a few news articles. This I was very excited to see. API security is one of the big problems with apps and websites, and Cloudflare is jumping in. So they're going to offer API Shield, and I just glanced through this quickly, but it sounds like what it does is cryptographically identify the clients with a certificate before letting them use the API. So it sort of adds SSH type authentication to an API, which is a really good idea. It sounds to me like it might not be practical to deploy this for all your customers, but anyway, it's a thought. APIs are the number one of the web application top 10 vulnerabilities. I think they have changed the rules this time so it doesn't appear there, but the top vulnerability in a phone app is not on the phone; it's on the server. And that's what I found. The most horrible security problems come from poor application program interfaces that let you do things like ask about other users' data and give it to you without authentication, and similar foolish things like that. So some kind of additional layer of security added there with a cloud security base like Cloudflare is a good idea. The great thing about layers of security and cloud-based security is a company can deploy this without making all their developers write better code. Even if your developers continue to write insecure code, you can put another layer in front of it, like web application firewall, and it will stop some attacks. So Windows 10 does have some machines running on ARM, although I don't know how many of them really are. I know I had a Windows 8 ARM tablet at one time. But anyway, I'm not sure about Windows, but I know Mac says they're going to move everything to ARM. And what a lot of people say is that's no good because none of the old apps will run, but they just need an emulator. And apparently they've had a 32-bit emulator on Windows on ARM for a while, and now they're going to have a 64-bit emulator on Windows on ARM. So that will presumably mean that you can use old apps. They'll probably not be quite as fast, and there will probably be some bugs. But anyway, it'll make an ARM machine more attractive. I'm very interested in getting an ARM machine. I like ARM assembler, but you do have to have some way to run old software. I'm used to on Intel-based Android, I run an ARM emulator in my Android virtual machines to run ARM apps emulated on x64, so I know it can go the other way too, and it really isn't that bad for simple things. This guy is coming up on Monday. Please come to that. It's worth extra credit. I'll try and remember to show that later when everybody's here. He'll be pleased if we get large attendance. So anyway, here's the job growth for each recession. These are the big famous, 2008 was the famous one, maybe 5%. And the coronavirus is huge compared to all the rest and very, very uneven. The highest earning people are actually doing better than ever, ones that can work at home and have high tech jobs and stuff. And the poor are doing very badly. And this, I think, is how we have the strange situation. The stock market keeps going up because the stock market is not the whole economy. Stock market's only the rich people that own stock. There's the people in service industries and such have lost their job, and they're not getting any bailout from the government either. They seem to have just given up on that. So it is pretty horrible. I mean, the government tells you to stay at home, they shut your business, and they don't give you any welfare or anything. So what are you supposed to do? It's not a good time to be poor in America. So the extreme measures that the Republican Party is taking, because they know they're going to lose big, are just getting out of hand. And this is what happens. The people that study the collapse of democracies into totalitarian states, authoritarian states, say this is how it works. The leader starts just blatantly breaking the law, and when they observe it, they're getting away with it, which Trump has been wildly getting away with the last few months, like Republican National Convention in the White House, complete corruption, using the established government to push his reelection. And now they're just trying to stop the voting. So the Texas governor is shutting down the drop-off sites. Only one drop-off site per county, so people will have to drive hundreds of miles to drop off their ballots. It's good. Yeah, sure. I saw that. Yeah, just go to samsclass.info and I'll have the Twitter information there so anybody can join. Good. Anyway, so that's pretty harsh and definitely suits voter suppression. And another, so there used to be rules prohibiting the southern states from engaging in voter suppression, but the Supreme Court removed those in 2013. So the Voting Rights Act was effectively neutralized, and now they can pass bigoted laws blocking votes with more impunity down there, and they're like this, and they're vigorously doing it. And the other thing, this will be the first year when the Republican Party is freed from a 40-year moratorium on sending people to go to election places to intimidate voters and scare them away from voting, which is what Trump announced during the debate he wants his people to do, like the Proud Boys and stuff. He wants them to go to the voting places and watch what's happening. And in practice, what this means is they look for people who are racial minorities there, and they threaten them with their guns and otherwise and beat them up and just drive them away so they won't vote, which is an old standard technique in America. And they will be doing it again. They're released from the freedom. Presumably, we can expect quite a bit of that this time. So it's going to be a real wild election. And at the end, it may just be ignored entirely. So here's another one. There's food aid from the Agricultural Department that goes to people that need food. And Trump is now holding up the program because he's demanding that every box of food have a letter from him, signed by him, to promote his political campaign, which is, again, blatantly illegal. And in fact, it's so illegal that many of the distribution houses are now stopping their work because even when they have orders from the president to do this, it's probably illegal for them to do it. And their distribution site can be shut down because these nonprofit distribution sites have to not be doing political campaigns. It's part of the law. It's part of, I think, being a nonprofit agency and such. So they're now stopping their work to call in lawyers and stuff to try to figure out what to do. Because when you get an order from the president and the order commands you to break the law, for which you'll be liable, then you don't know what to do. I remember when I worked in a financial business, I got an order from the owner of the company to break the law. And I went to the second in command and I said, you know, I can get another job. I'll quit. I'm not going to break the law just because the boss told me to. But, you know, it does put you in a bad position when you get illegal orders. Same thing for military, like clearing the people out of the park in front of the White House with tear gas so the president can go stand in front of a church or a photo op for a campaign event. That's also completely illegal. And the military people that did it had to apologize later and say they're not going to do it again. The military is extremely sensitive about being used for political purposes against United States citizens. This goes all the way back to Rome and Julius Caesar. There's a perennial problem in nations that the commander-in-chief of the army just takes the army to declare himself king and kill off his opponents. And their military has very strong rules to try to prevent themselves from being used that way, which still appear to be holding up, although very little of our system is still holding up. So Trump has been ridiculously claiming that the next election is going to be fake with no proof at all. And this is what Republicans have been doing for decades, is claiming that there's all this voter fraud, which there isn't, and therefore they can engage in voter suppression. So anyway, it's interesting to see. There's a very strong attack on our voting system, and what the Russian people, the people who left the KGB and stuff, have said it's amazing. He's doing exactly the Russians' job for them, which is right from the beginning. Trump has been doing exactly what Russians want, convincing Americans that our democracy is no good, our system is no good, and we shouldn't bother voting, and the leader shouldn't bother having policies, and the leader shouldn't bother obeying the law. He should just be a dictator and do anything he wants, and you should just obey all the rules, which is the Russian system. Just follow Putin. So one thing that surprises people is a lot of companies are now taking political stance, but the really rich people, the multi-billionaires, are not taking any positions in a presidential race. And that's both because they probably don't want to take a position that could blow back on them after the election, but it's also neither side wants their endorsement. The current political winning strategy is to pretend to be a poor, normal, honest working man. And if a multi-billionaire was to endorse you, it would probably work against you rather than for you. So these people are not endorsing anybody, and nobody wants them to endorse anybody. It's an interesting issue. So Russia is doing what Trump wants to do here. They are rushing their coronavirus. Oh, Mike Bloomberg. Well, Mike Bloomberg, has he actually endorsed Biden? Yeah, I think he has. But Mike Bloomberg actually ran as a campaign. He ran as a candidate. So I think he took an explicitly political position. And yeah, right. Mike Bloomberg certainly has taken a position. You're quite right about that. Anyway, so Russia has this thing, they called it Sputnik 5, which is not a mistake. The point of their vaccine They are making the vaccine and already handing it out because they skipped phase 3 trials. They did not bother to prove that it was safe or effective. They're just distributing it based on early tests, which in the medical community are not considered enough proof to make it safe or effective, but they are distributing it, and they're calling it Sputnik 5 because the point is to build up Russian pride, just like the original Sputnik did. Russia got the first satellite up there, which greatly humiliated the United States, which then had a big space race to catch up. And they're going to have the first vaccine out there, which is another public relations coup if it works. If it turns out to have a defect, then it won't be such a good idea. But anyway, they're rushing it out. And this is, of course, what Trump is very much trying to do here. He's still saying that we're going to have a vaccine out before the election, which you could only have if you skip the trials to make it safe and effective, which is what he wants to do. And he may be able to pressure the CDC into doing that. We will see what happens. Anyway, so the GOP put out an ad claiming that this Democratic congressman was trying to end the sex offenders registry and make it so that registered sex offenders would be around you and you would never know. And so people are hunting him and his children and stuff on death threats on the internet from QAnon and such, which is certainly what happens from these things. So it's the online conspiracy theories do have a lot of victims. GitHub for free will scan your code for vulnerabilities, unsafe deserialization, and so on. This sounds like a great idea. There's an enormous amount of unsafe code on GitHub, and having a free, easy feature would be great. So I'll see if I can get this working. I'd totally like to have projects where you put up code with various vulnerabilities and turn this on and see what it can detect. My previous experience with vulnerability scanners has been very discouraging. They really aren't very good. They don't catch very many vulns at all, but they do catch some. And it would be good to test this on a few cases and see how good it is. I like the price. Free things are important. So there was Coinbase. I think I talked about in previous classes. Coinbase, the CEO put out a statement that we are not going to make any political statements at Coinbase. If you want to have some political or ethical or social thing you're doing, just leave it at home. Work, we're just going to do work. Now, this is the way every corporation was 20 years ago and before. The business of business is business. You shouldn't be trying to be a do-gooder or do social, equality or anything. But this is very controversial these days. Now it is much more expected for companies to be socially aware, pushing they're at least supposed to engage in virtue signaling where they pretend to care about things. So Coinbase has now offered an exit package to give people a golden parachute if they want to quit the company, since they are not going to bother to attempt to be socially good. And he's just saying, you can just leave if you want us to take political positions. And the ex-CEO of Twitter said that he should be lined up in front of a firing squad for removing the morals from his business, which is, in the spirit of Twitter, one of these outrageous things to say. But anyway, this is an interesting evolution of the American business community. I know the Salesforce CEO wrote a whole book and pushes a policy that you should be a socially responsible company, and you should think about the citizens in your town, even like the homeless people and stuff, and you should arrange your business to benefit them, which is absolutely different than the old-fashioned business school, where the only thing you care about is making money for your stockholders by any means necessary, and you don't care about anything else. It's a more modern philosophy, and you're seeing some battles here on the two sides of it. So anyway, I'll just mention again, on Monday at 6 p.m., please tune into the same Zoom channel, and we'll have the CEO of FireEye, the CSO of FireEye, Chief Security Officer, a very important company. Anyway, let me get to the cryptography. So today it's hash functions. All right. So we're going to talk about what a hash function is, what makes it secure, and then the SHA family, SHA 0, 1, 2, and 3, and then Blake 2, the latest and greatest, and a few things that can go wrong with hash functions. And you've already been playing with them quite a bit in Pollard's Row and quite a few of the projects. Hash functions are one of the essential cryptographic types that you have to do modern cryptography. So, all right, so you need a hash function to have a digital signature. The public key encryption uses them. It labels the certificates with them anyway, and user message authentication and verification of integrity on files and such. And of course, you use them to make hash functions for password storage so that you don't store passwords in a reversible form. And so the point is to make a fingerprint of a file. You put in input of any length, you run it through the hash function, and you get a short fingerprint of a file, something like 256 or 512 bits. And that is intended to be a unique identifier of the whole file. That's the idea. Just like a fingerprint, that will uniquely identify the original message, even though it's typically much longer. Now, there are some old hash functions which were used in something called hash tables. And the point of these was basically just load balancing. If you were going to have a large lookup table of things, a big array, it turned out that if you scrambled the inputs before looking things up, you had a more even distribution of the time it takes to look things up. And so that was the old-fashioned hash table, to just sort of scramble things. It was not intended to be hard to reverse or hard to forge. It had a different purpose. So these are things like CRC. The point of cyclic redundancy check, which is used in Ethernet at layer 2, is not to resist an active attacker who is attempting to forge a signal, but simply to detect if you have lost a bit in the transmission on the wire. If you lose a bit or two, then it will change that value and you can detect it. That's all it's intended to do. But secure hash functions are intended to be trustworthy, so that if the hash matches the expected value, you have some high degree of certainty that the message has not been altered. And there's not even a malicious way that a person could carefully calculate a way to alter it. That's what you'd like. So, for example, if you want to sign a message, you typically hash it and use the hash to make the signature, so you don't have to deal with a long message. You have a short thing, which you can then sign. And if your hash function is secure, then signing the hash is as good as signing the whole message. So you must have unpredictability. So if you take SHA-256 of A, you get this, and B and C, and you can see if you change just one bit, like going from A to B, it changes everything. So there's no pattern. You can't change the input a little bit and see a small little localized change in the output. It has this dispersion, which is good. That's what you want. Now, the problem with hash functions is they are intrinsically non-unique. So suppose I have a 1024-bit message, which is not very long, and the hash is 256 bits. Well, then there's 2 to the 1024 messages, but there's only 2 to the 256 hashes. Now, those are both ridiculously huge numbers, but the first one is much bigger than the second one. And I didn't count them, see how long they were. These should be, for 256, these should be exactly, what, 64 bytes. Is that 32 bytes? 32 bytes, so 64 characters. Yeah, maybe this image is chipped off and all. It should be exactly the right length. Yeah. Anyway, so the point is, this means there are many, many messages that must go to the same hash value. You have more messages than hash, so that means there really are multiple messages that have the same hash. So your hashing is not unique. Intrinsically, because the hash is smaller, you know that there are multiple messages that share the same hash. So it is impossible for it to have this desirable property where knowing the hash means perfectly that you know what the message is. But what you want is you want it to be so rare that 2 messages will have the same hash that you can, in practice, neglect that possibility. So this is the point. Now, hashing should not be reversible. You could not be able to take the hash and deduce the message from it. It's not like encryption, where there's a decryption algorithm. There is no key, and there's no, in principle, no way back, because in principle, many messages hash to the same thing. But what you want is you want there to be, the hash to be so long that you can't find messages that have a collision. So here's the simplest kind of attack, is pre-image resistance. If I give you a hash value, like say all zeros, can you find a message that will hash to that? And your hash is considered strong if you cannot do that in practice. That is called pre-image resistance. Can you create a message with a specific hash value I tell you? And you should not be able to do that. All right, so the simplest way to do that is to just take random messages and calculate hashes until you find it. So in this case, you would have to take 2 to the n guesses. So if you have 256, you'd have to do 2 to the 256 calculations before you would get one of these to work. And that's an impossible number. We mentioned before, 100 bits is essentially perfect security. Anything that would take about 2 to the 100 calculations is very secure, because that's more than all the computers you could ever afford would ever be able to do. So second pre-image is almost the same thing. However, instead of giving you a hash, I give you a message. You hash that message, and I say, there, can you find another message that hashes to the same thing? And this is essentially the same as the previous thing, except instead of giving you the hash, I give you a message to hash, and therefore just as hard. The only reason why it's important to mention it is because there are some hash functions that have a defect, like a linked extension attack, where you can carefully create a pair of messages that will hash to the same value without doing 2 to the n calculations. All right, so every hash function in principle has collisions. If you could run computers forever and try enough, you would eventually find 2 inputs that have the same output. And that's because of the pigeonhole principle. If you have 10 holes and 11 pigeons, then there must be at least 1 hole with 2 pigeons. And we have many, many more messages than hashes. So in principle, there exist messages with the same hash. All right, it's just you want it to be that they're so rare that you cannot find them. Now, if you want to get a hash to equal a specific value, that would be like if I took a classroom and said, do we have somebody here born on January 1? And there's a very small chance of that unless the room has around 360 students. But if I said, are there 2 students with the same birthday? Then I'm trying to get a collision, but not a collision with 1 value. If I have n students, I have n-1 possibilities of collision. So the first student could match the second, and the first could match the third, and the second could match the third. And so that's the point here. If you have 23 people, you're more likely than not to have 2 people with the same birthday, because you only need the square root of the number of possible values for random numbers to collide. And this is the same thing we had with Pollard's row. If you go through a series of hashes, you typically only have to go to about the square root of the number of possible hash values before you will hit a loop and hit a collision. That's the birthday attack. So if you search for collisions, and the simplest way is just calculate hashes of numbers that are essentially random, and then remember them all. And every time you calculate a new one, go back and see if it's on the list. Now that would work. You'd only have to do 2 to the n over 2 hashes, but you would have to remember 2 to the n over 2 hashes. So that's the naive birthday attack. Compute them all, store them in RAM, search the list every time. And so you need 2 to the n over 2 calculations and 2 to the n over 2 units of storage. But it turns out in practice that the storage is too expensive for this to work for modern hash functions. For MD5 though, which is 128 bits long, then if you just tried to match an exact hash value, you'd have to do 2 to the 128 calculations. So the simple first preimage resistance, MD5, is very strong here. Even though MD5 is considered broken, it's not broken in this regard, that you can just create something that will hash to any number you want. But what you can do is find collisions. All right, and like I talked about, this is the thing I talked about before, 56-bit keys were broken in the 90s, 64-bit keys were broken in the early parts of this century, and 72-bit keys have never yet been broken. So 100 bits is considered a pretty good number. If you have 100 or more, you're pretty safe. Nobody's getting in there. 80 bits is considered not safe against the Bitcoin mining. Bitcoin mining is a place where you can see how people are really putting a lot of money making things as fast as they can. And there are some beliefs that the total number of Bitcoin mining is now up to maybe 2 to the 88 in a year. So in principle, if you could get all the Bitcoin miners to work on cracking something, they might be able to crack an 88 or 90-bit key, but not 100. All right. So here's the preimage attack. So if you assume the maximum computing power available to anybody is, say, 2 to the 96, right up here. That's apparently the maximum number of computers anybody can find in the whole world, because the Bitcoin miners are essentially highly motivated to make the fastest computers in the world. Then a preimage attack would take 2 to the 128, so you have a safety margin of about 230, 2 to the 34, something like that. So 2 to the 30 is a pretty big number. That's your safety. All right. And all right, so that's the naive birthday attack. Now that was the preimage attack. Now the birthday attack, you do 2 to the 64, calculate the hashes, so you make 2 to the 64 units of RAM. And so here, 2 to the 64 bits of RAM is 16,000 petabytes, and all the RAM in the world is only about 3,000 petabytes right now. So you have about a factor of 5 in principle. So if the whole world dedicated all the resources on Earth to doing that attack, you would be within a factor of 5 of succeeding. So that's not very good. That's not a high safety margin. That just means if somebody finds a trick to make it a little bit faster, they'll win. All right. But for the preimage attack, it'd be 2 to the 128, and that's a ridiculous thing. You never do that. So those are the calculations of how safe it is. And of course, MD5 was never approved by the government for any purpose. MD5 is not considered secure by any means, but it's not so broken that you can just easily create a file with any MD5 you want. It is broken, however, that you can use a length extension attack and make pairs of files with the same MD5, and that can be done pretty easily even on a normal computer. So we talked about the row method. You calculate hash and hash of hash and hash of hash of hash, and you have a series of numbers here, and eventually it'll hit a loop. And you could remember them all to get there, or you could remember every 10th one, or you could just remember every one with the power of 2 steps, or you could do the tortoise and the hare, where one takes 2 steps at a time and one takes 1 step at a time. There's plenty of ways to notice when you're in a loop without having to really remember everything. And that's the various versions of Pollard's row. And you've got the projects where you're doing that. So the result is you can find these collisions where 2 numbers are the same in a way that doesn't require much memory and that doesn't require much processing time either. Any way you cut it, you typically only have to do about the square root of the number of calculations if n is the total number of bits in the hash. Instead of doing 2 to the n, you only have to do 2 to the n over 2 calculations or so before you'll hit a loop. All right, and so you've done the projects here, you've done it for various lengths of hashes. Let's take a look at the Cahoots, which should be here. Here. And this is 9A, or is it 141? All right, let me figure out what I'm doing here. 141.6A, all right. Okay. Helps if I have the right ones. All right, give it 10 more seconds. All right. All right, what hash functions have collisions? They all have collisions in principle. You cannot have a hash function that does not have collisions. All you can have is a hash function where the collisions are so hard to find that none have been found yet. But in principle, there are always collisions. How many calculations will it take to find a message that hashes to a specific 32-bit hash number? Two to the 32. You will, if you're just trying to get a specific number like all zeros, you're going to, in principle, have to try 2 to the 32 guesses before you'll hit one. All right, how many calculations will it take to find a hash collision for 32-bit cache? That's it, the birthday attack. By the time you calculate the square root of them, 2 of them will match. So finding a collision, as long as you don't care what the value is that collides, is much easier than matching one particular value. What methods use more RAM but less CPU? That's what rainbow tables are. You have pre-computed tables to look up some of the math in, so by using more RAM, you need less CPU. What method uses more CPU but less memory? The row method that we talked about, but you don't bother to remember all the ones you calculate. You only remember some of them, and yet you can still find the collision, although you will have to go more times around that circle. All right. And which method uses more RAM and more CPU? That's blockchains. Blockchains mean you make 1 million computers repeat every calculation, so you use tons of RAM and tons of CPU until you're using up a vast amount of power. It's a way to make computing much, much more expensive. But the benefit supposedly is that nobody has to trust anybody. All right. All right. All right. Pop, let's tell me who they are. Shaw as well, I reckon. All right. Aha, pop. Okay, good. Anyway, let's go back here. And, all right. So to make a hash function, I see who Shasha is. I'll record it later. All right. So you typically do it with iterations. You break your message into blocks, and then you process each block. So this is the Merkle-Damgard construction. This is what most of them do, MD5, SHA-0, and SHA-1 and SHA-2. I don't know why I got MD5 in there twice. Anyway, you put in a block of data and compress it. Then you use that and the next block of data and compress it again and that and the next block of data. So you just keep adding block after block until you're done, sort of like doing cipher block chaining with AES. Only in that case, you would output a block every time. This time you just keep feeding it all in. So at the end, you just have one block. So it's small, one block size worth of data comes out at the end. Now this means you'll have to pad it since you have a block of data. So if I was to use a 8-bit message, the rule SOF356 uses 512-bit blocks. So it pads with a 1, then a lot of zeros, and at the end it puts the length of the original message. So that's the pattern to pad things. All right, so use a block cipher to build a compression function. You use the block as the key. You feed in the message and encrypt it, and then you take this and XOR it with the output, and that means you can't use decryption because you've added an extra step that mixes some data before the encryption and after. So even if you know how to reverse the encryption function, it's not going to work anymore. So you can take the mathematics that you use to design a block cipher and easily modify it to use it for a hash function. All right, there's other kinds of compression functions with various other ways of mixing the input and the output, and they're all available, but they don't turn out to matter that much. More complicated, and the first one seems to be good enough. So that's the compression type block hash functions. The other type is a sponge function. And again, there's no key check, which is SHA-3 does it this way. So what you do is you have an internal state and you XOR the message block in, you permute it, and then you XOR another one and repeat it for all the message blocks. This is called absorbing it. So you create an internal state that has somehow digested all the input from all the input blocks, and then you have a squeezing phase where you squeeze the hash function out of here. So this is kind of weird. You sort of fill up a sponge with water with all the input data, and then you squeeze out as many bits as you want. You can actually get different hash lengths depending on how you perform the squeezing phase. So that's the game, and the internal state is kind of big. So the SHA family, MD5 is where it started, and like I say, you can generate MD5 collisions fairly easily, but you cannot perform the preimage attack on the first preimage attack where you generate an MD5 to match any value you want. But so SHA-0 was originally approved in '93, but it was rapidly discovered to be unsafe and replaced by SHA-1. And they did not publish what was wrong with it, which the NSA tends not to do. But people figured it out independently in 1998. And they found, in principle, this was 160 bits long, so it should take 2 to the 80 calculations to find a collision, but they found an attack that lowered that to 2 to the 60. And then later they lowered it to 2 to the 33, which is ridiculous. 2 to the 60 is in principle possible, but not for a single home computer. 2 to the 33 is easy, even on a home computer. So that turned out to, that totally destroyed SHA-0. So SHA-0 never became popular at all. But as we know, SHA-1 became the industry standard in almost everything, used it for a long time. So this uses an encryption function, and it just keeps encrypting it. The message, the next block of message, and the hash from the previous one had the next one, just runs it over and over. And so it's doing it with an internal state that is 5 32-bit words, and it just scrambles them with this fashion. So that's the plan. And so SHA-1 held for a long time, but it was broken in 2017 by a team involving people from Google. They found an attack that would lower it from 2 to the 80 down to 2 to the 63, and Google was able to donate enough computing time to actually do 2 to the 63 calculations, which is a pretty big number, but not impossible. And so they did not do the preimage resistance attack where they actually generated a hash of a specific value. They just found a collision. They found 2 PDF files that would hash to the same value, but you could open them in a PDF viewer and see that they were different. So it worked. It was a linked extension attack, essentially. So SHA-2 was designed to be the replacement of SHA-1 because people saw this coming. Long before Google did it, they knew since 2005 that SHA-2 was no longer going to be trustworthy because this math had been done showing that there was a shortcut to save you a monstrous amount of time. So everyone was warned, we have to knock off SHA-1 and move on to SHA-2. So SHA-2 is all longer than SHA-1. At least 224 bits. The most common types are 256 and 512. It's got 8 32-bit words internally, and all of these are considered quite strong. The problem is the underlying fundamental mathematics is similar to SHA-1, so people are concerned that the vulnerability might be found in it like was found in SHA-1, although that has not happened. So SHA-3, they had a contest to determine SHA-3, and this has happened, so we have SHA-3 available in case we decide we don't trust SHA-2, although right now, nobody has found anything wrong with SHA-2. And here were the finalists, and just like the other cryptographic algorithms we talked about, they have a big contest for years. Mathematicians submit their functions, they attack each other, and so if you like the government, you will go with the one the government officially approved, KeyCheck. And if you want to do business with the government, you'll do it. And if you don't trust the government, then you choose one of the other finalists because all the finalists are considered very good. Just one of them is given the government stamp of approval and becomes a US standard. So it's now a sort of political statement, whether you'd rather go with the US standard or avoid going with the US standard. All right, so the US standard, KeyCheck, is SHA-3. And it's completely different. It's a sponge function, 1600 bits internally, and it's got extensible output functions. So you can make hashes of any length. And so Blake 2 is the one that is as secure as SHA-3, but much faster. This is in fact faster than MD5 or SHA-1. So it is considered the new advanced superior hash function. It was one optimized for 64-bit platforms and one optimized for shorter, like 32-bit platforms. And here's how fast it is. Millions of hashes per second, I think. And it's much faster than anything else. Here's MD5, SHA-1, here's SHA-2, and it's faster than any of them. So in principle, Blake 2 is the new hotness. and it's being used in the newer cryptographic functions. Although you could continue to use SHA-2 and it would be fine, it just would not be absolutely the most efficient thing to do. If you're using SHA-2, in principle, you could get more done for cheaper by switching to Blake-2. But most people don't really care about that much efficiency. So it's got a counter and a flag, and it's using Cha-Cha, which is based on Salsa 20 that we talked about before. These are the newer, considered more secure and more efficient cryptographic algorithms. As I mentioned before, I don't emphasize them much in this class because I think for most of us, it would be perfectly fine to just use the normal stuff like AES and SHA and RSA. If you use those correctly, your stuff will be plenty safe. The advanced stuff is slightly better and faster, but just using the standard stuff correctly would make you pretty secure enough for almost any reasonable operation these days. But here's how Blake 2B works. You have 464-bit words, and you have these operations where you're shifting them by a certain number of bits and then adding them together and adding message words, just scrambling them together. And all the cryptographic operations, all the algorithms we're going to study are like this. They just combine the very simple little operations like little tools, do an XOR, do a shift, do a matrix multiplication. There's really only 3 or 4 transformations. And you mix them up in a carefully chosen mix that is efficient, fast to compute, and accomplishes your goal. And for a hash function, you're just trying to create a unique function that will be not related to the input and that won't have any findable collisions. So there's things that can go wrong. For example, you could use something ridiculous like a CRC32 for file integrity without understanding it was not good enough for that. It was never intended to do that. It cannot withstand a malicious attacker carefully crafting data. It's not a cryptographic hash algorithm. This is what I've complained about so much about Android apps. I find people just using the wrong cryptography. That is just the wrong tool for the job. That's why I think people just need to know how to do the standard stuff correctly, and it will greatly advance our industry. Then there's the linked extension attack. A lot of hash functions had this structure where you break the message into blocks, you process the first block, you take that output and process the next block and the next block. And what this means is if I have a message that hashes to something, I can add something to it, and I can work from the previous hash without ever knowing the previous message. So this turns out to be a weakness. I can craft hashes from previous hashes, and that, depending on how your software interprets the hash data, this can turn out to be a big problem. So if the original message is padded, it's a message 1 appended to padding. But if I extend the message, I now have message 1 padding and then message 3, which is not what you'd normally expect. So it just depends on whether your application is smart enough to notice that this padding is in the middle that really shouldn't be there. Many things are not. One example that we've had in previous classes was talking about the cipher block chaining attack. Is if you consider a web application, you'll go to like company.com/page.php ? Now you have data like user ID equals something and password equals some junk, and then other things like date equals ampersand date equals some stuff, and then ampersand price equals some stuff. Okay, and so if I was able to take some short version of this and then extend something to it that was under my control, even if I was to put something out here that didn't belong here, like the UID way out here, there are plenty of applications who will in fact not notice that the same thing has been defined twice. They will not even notice if something back here is all garbled and wrong. They won't know or care. They'll just pick this part and use it. So attacks that let you control only part of the data turn out to be quite effective for some applications, even though you won't really have the ability to forge the entire thing. And that's what happened here. Some applications can be fooled by a linked extension. All right, So SHA-2 also has linked extensions. It's vulnerable, which is a shame. If you had done this process where you hash one, you compress one, if you just made the last compression function different, then you wouldn't be able to do a linked extension attack. Because if you now tried to add more stuff to it, this one wouldn't be the right operation. So it would have been easy enough to design SHA-2 so it was not vulnerable to this, but that was not done. And now it's a standard. Blake 2 does that. It's not susceptible to linked extension attacks. So anyway, that's one vulnerability. And so here's, for example, here's one thing you could do. You could have a cloud server like, say, Dropbox. If you put stuff in your Dropbox, Dropbox will give you 2 gigabytes of storage for free, and Microsoft will give you something like 100 gigs for free in OneDrive. Now, how can they do that? The way they do that is everybody pretty much stores the same stuff. They copy MP3s, and things like that. So if you store an MP3, it doesn't really make a copy of your MP3. It just says, well, I've already got a copy of that MP3 in somebody else's Dropbox, so I'll just connect you to the same MP3. So when you ask the server, do you have my file? It looks for the hash in a table of hashes to see if it has that file. And it doesn't actually go check to make sure the file is there, it just makes sure the hash is there. So here's what this might do. You put up a challenge, it calculates hash of message plus challenge of response and sends it back. So if the server gives the right response, that means it has your file. But with a linked extension attack, you can keep only the chain value from the message. It can store the hashes, but not the files. And now it will be able to calculate this response, even though it no longer has the file. So that's one of the many weaknesses. And like I say, that's why this linked extension vulnerability only matters if you apply the hash in a way that doesn't take that into consideration. And of course, there are other ways to do it. If you had just calculated challenge before the message instead of after the message, then you would not be able to calculate this without having access to the original file. So, that's why you have to understand the cryptographic functions. It's very easy. What naive people do is they scramble something with cryptography, it looks terrible, and if they can descramble, they say, well, that proves you have the key, that proves you know everything, because nobody could possibly make a scrambled mess that would pass a simple test. But as we can see, you often can pass certain tests, even though you really are not the authenticated person that has all the private data you're supposed to have. So anyway, let's take a look at the last cahoots, which is 6B, I think. This is 6, right? Yeah, okay. I've got a name to record. There could be message padding, Chaz. The issue there is if you only are adding more data to the end, then the linked extension vulnerability is likely to matter. This is why, I think the author of your textbook actually made Blake 2, and if people used Blake 2, they wouldn't have to worry about this. Anyway, I guess we can go. All right, which hash uses a sponge function? That's SHA-3, all right? All right, which hash uses Merkle-Damgard? They all do. They're all similar in construction, which is why we have SHA-3. All right. Which one uses key check? Which I might be pronouncing wrong. Anyway, that's SHA-3. All right. Which hash collision was found in 2017? That was SHA-1. Google broke it. All right. What's the fastest one? Blake, you know, this is real progress in hashing. It's the most secure, the strongest, and the fastest. That's why I think the author is understandably proud of it. All right. All right, that's person has won before. And so has that one. And that one will have to tell me who they are. All right. I see a name there. All right, good. All right, well, I think you folks have got a lot of projects to do. I'm going to stop the recording and put it up. I'll stick around to answer questions.